Lesson 80 is more with inverse trig functions, and before you get started, make sure you look at the inverses of the reciprocal trig functions that are listed at the beginning of Lesson 80. You might also want to review Lesson 68 and the inverse trig functions that we did there: inverse sine, inverse cosine, inverse tangent. And we also looked at 1 over each of those, the graphs of those, the reciprocal functions. So we looked at the graphs of secant, cosecant, and cotangent. So what we're doing here is we're looking at the inverses of secant, cosecant, and cotangent. We're looking at reciprocal trig functions and their inverses. The inverse of a reciprocal. So that is like the most confusing of all of the different types of trig function graphs, which is also one reason we've saved it to the end here, so you've had plenty of time to build up to this. So again, there's symbolic and graphical forms. Those are shown in the rules section for Lesson 80. And as with capital arc sine, capital arc cosine, capital arc tan, the ranges of arc secant, arc cosecant, arc cotangent, those are particularly important. And if you look at those graphs compared to the graphs of just regular secant x, regular cosecant x, the arc secant and the arc cosecant, those seem to kind of stop abruptly, and one reason for that is the same as the reason arc sine and arc cosine stop abruptly. If they continued, they'd be relations, not functions. Instead of just talking about those comparisons of the reciprocal functions and their inverses, let's look at those graphs again. Look at secant x. Switch x and y. That's what inverse functions do, right? And you get that function below, the secant to the -1 function there. Also capital arc secant, also known as that. Look how secant x, it passes through the y-axis there at 0, 1. We switch x and y, it touches the y-axis at 1, 0. So that's included. That point is included there. We can assume that. And then in secant x, there's an asymptote at pi over 2, which ends up being a horizontal asymptote on the inverse function. Think about it though. If we continued those patterns onward, we try to do the vertical line test through it, we get a relation, not a function. Look at cosecant x. The vertical asymptote at 0 becomes a horizontal asymptote at y equals 0. It was at x equals 0, now it's at y equals 0. There's a trough there on the cosecant function at pi over 2, 1, right there. Switch that to 1, pi over 2. What do you get on the cosecant to the -1, or the arc cosecant function? You get that point right there, so that's included. Notice the range though, if you're looking at it that way, the range is discontinuous, right, because of that horizontal asymptote. It goes from 0 up to pi over 2, and then it also goes from 0 down to negative pi over 2, but you don't include 0 in either of those. There's different places we could have defined this as a function, but it's always with respect to 0 in there somewhere. So it's a function plus or minus pi over 2 from 0. That's just how we're defining that. And then cotangent, you can see there, we're going from a horizontal asymptote at 0 to a horizontal asymptote at pi, because we had a vertical asymptote at 0 here and a vertical asymptote at pi there. Refer back to these graphs as you need to. You may even want to sketch these in your notes so that you have a quick reference place for them, and it'll just help you get your mind around the different problems that we're going to do. Here's 2 things from Lesson 35 on inverse functions that will really help you wrap your mind around reciprocal trig functions and their inverses. And you may have noticed I talked about a little bit of these when we were looking at the graphs. First, a function and its inverse, they're symmetric about the line y equals x. So the line y equals x, that basically makes a 45-degree angle, right? So that's why vertical asymptotes in one function, in the reciprocal function, those are horizontal asymptotes in the inverse function, the inverse of the reciprocal. Because there's symmetry there, right? This one's 45 degrees from y equals x, and so is this one. Second thing, any point x comma y in a function, that'll be the point y comma x in the inverse function, unless that point is outside the inverse function's range. Okay, that's a big deal there. So, for example, cosecant pi over 2, that equals 1. That's what we were talking about earlier, that point right there. Then you think pi over 2 comma 1. Now for the inverse function down here, you think 1 comma pi over 2, right? So we've already kind of looked at that, but that's an important thing to keep in mind. So use the graphs together with the symbolic forms to carefully answer the examples that we're going to do. And then keep in mind too, just like in lesson 68, what we say lowercase arc, that's for relations, capital arc is for functions. So look at example 80.1. Identify each of the following as a function or relation. If it's a function, use interval notation to write the domain and range. And also consider the fact that the function doesn't exist at locations that appear to be asymptotes, so the interval notation would have a parenthesis, not a brace at those locations. So let's just go through these. A, that is a function, right? It's capital, arcsecant. So that's a function. Look at the graph again. We consider these closed circles there that it equals those locations. So for the domain, we're going this way from 1, starting at 1, and then we're going this way. For the range, we're just up and down right here, right? And up and down right there. We go from 0, including 0, up to pi over 2, but not including pi over 2, because that's like a horizontal asymptote right there. The vertical asymptote became a horizontal asymptote. And then we go from pi over 2 up to and including pi. So we say our domain is equal to parenthesis minus infinity to minus 1, close that off to show we're including that, and it's also including 1 onto infinity, like that. The range is equal to including 0 up to pi over 2, not including pi over 2 though. And again, not including pi over 2, and then stopping at pi, including pi, like that. Okay, B, just look at that lowercase and we say that is a relation. And then C, by the f of x, that's a hint that that's a function, but that's also another symbolic form for the function there. Arc cotangent, so that is a function. Let's take a look at that. The domain is all real numbers, right? There's no discontinuities there. And then the range from here to here, those vertical asymptotes, those become horizontal asymptotes basically. So it doesn't include 0 and it doesn't include pi, but it's everything in between those. That would be the range. So for C, we'll say the domain for arc cotangent, that equals, not including, because we never include infinity, minus infinity, comma, infinity. And then the range, that's equal to not including 0, not including pi, up to that. Moving on to example 2, evaluate f of x equals arc cosecant x when x equals 2. And write the answer in radians. So something you might want to keep in mind with this is the input to one function is the output to its inverse, right? The input to one function is the output to its inverse. In other words, the inverse of arc cosecant, what is the inverse of arc cosecant? Well, it's cosecant x, right? You can do that. You can take the inverse of an inverse function, that gets you back to the original thing, cosecant x. So if we can switch x and y here, we've been given for arc cosecant x equals 2. Well, that would be the output for cosecant. We'd say cosecant x equals 2. What is cosecant x? It's 1 over sine x, right? So we say 1 over sine x equals 2. We rearrange this and we get sine x equals half. And you know what that is, right? Sine 30 equals 1/2. We've been asked to write the answer in radians, so we'd say x is equal to pi over 6. That's what f of 2 is. Back to the original. That's what it has to be. Don't believe me on this? Look at the graph again. These graphs will help you get your mind around these. When x equals 2, 1, 2, we go up to that point right there. I mean, that seems reasonable, right? Pi over 6. If this is pi over 2 here, like halfway would be pi over 4. And it looks like it's less than halfway there. So pi over 6. That does make sense. Let's do one more. We'll be applying example 2 so you get a little more practice with that as well on this. But this says if f of x equals cosine x, g of x equals arc cotangent x. Figure out that composite function there. So you can tell the first thing we want to do is figure out what g of square root 3 is. So g of square root 3 when x equals square root 3. What's the inverse of arc cotangent x? Well, that's just cotangent x, right? So we can say instead of x equals 3, we can use that as the output, right? Cotangent x equals square root 3. What is cotangent x? It's the reciprocal of tangent x, right? 1 over tan x. So we're kind of following a format like we did in example 80.2 here. And that equals square root 3. Rearrange that. Tan x is equal to 1 over square root 3. Where does that happen when the opposite side is 1 and the adjacent side is square root 3? Well, that happens at 30 degrees, right? Think about your lesson 16 rules on this. Think about that table of trig ratios in the lesson 16 rules. If you don't have that memorized yet, even though we're almost done with the course, it'd still be a good time to try to memorize this. Just make your math go faster for you, I promise. Especially, you know, instead of trying to do these on your calculator and messing with 1 over square root and all of that, just think about unit circle related things. Lesson 16 trig ratio values here. Tan is opposite over adjacent, sine over cosine. So if tan x is 1 over square root 3, that means x is pi over 6 or 30 degrees, however you want to do that. And so now that x value, that's the output of g of square root 3, right? Going back to the original inverse function that we were dealing with. So that's what g of square root 3 is. So now what we're doing is finding f of 30. F of 30 degrees is equal to cosine 30 degrees, which equals the square root of 3 over 2. And that's our answer. Be careful on these. Just follow that logic of a reciprocal function, what that is, an inverse function, what that is. Use those graphs as you need to help get your mind around where you are with these functions and just working with that relationship between the symbolic form and the graphical form. Okay, well that's all for lesson 80.